Generative AI offers the promise of infinite scale. You can produce thousands of articles, reports, and communications in seconds. But in enterprise environments, this volume comes at a severe cost: the complete erasure of domain expertise. When organizations deploy standard zero-shot prompting models to manage complex services, the output degrades. These models lack the historical context required to understand the nuances of a specific business or discipline. The result is a flattening effect. A brand's highly tuned human expertise, the distinct vocabulary, the rhythm of thought, the specific pacing of an argument, is averaged out into a generic aggregation of text. Operationally, this leads to disjointed workflows, a lack of cohesive strategy, and immediate resistance from teams who recognize the output as hollow. To solve this, a structural countermovement is emerging across the industry, often referred to as soulful AI or agentic resonance. Achieving this level of resonance is not a matter of clever copywriting or finding a hidden prompt engineering trick. It requires a specific, customized architectural deployment. Instead of interacting with a raw model, organizations are building containerized digital studios within cloud environments like AWS Bedrock or Google Cloud Run. These studios act as rigid command hubs designed to govern the AI. Preserving human intent at scale is a systems engineering problem. It demands strict data boundaries and bifurcated models to ensure the system operates as a reliable publishing partner. The primary roadblock to deploying these systems successfully is almost never the technology itself. It is disorganized, mislabeled, or non-existent historical data. Implementing a functional enterprise AI requires front-loading the effort. 80% of the work lies in cleaning, structuring, and preparing the data, not in tuning the large language model. This requires an Intel-grade strategy. Before the system can accept a single user query, it must ingest a deep, proprietary history of the creator's or organization's past work. This process maps the vocabulary preferences and rhythmic cadences of the human creator. But it must also map negative constraints, identifying the exact words or logic paths it is forbidden to use. These linguistic weights and negative constraints are loaded directly into the LLM's context window, acting as an unbreakable operational boundary that dictates every output. Grounding the model in this rigorous data foundation stops it from functioning as a generic content generator. It becomes a strictly constrained, high-fidelity mirror of its creator. The Vionde Studio architecture provides a blueprint for how this constrained model operates within an automated, multi-stage publishing workflow. To prevent output degradation, the AI is explicitly configured to act as a sparring partner, instructed to critique input rather than acting as a yes-man. In Stage 1, editorial review, the system actively scans the human's input. It flags logic breaks, identifies duplications, and highlights where arguments are too shallow. Stage 2 handles SEO resonance and title ideation. Here, the system evaluates potential titles by balancing algorithmic search visibility against the author's authentic tone. Stage 3 executes metadata automation, generating the necessary back-end tags, alt text, and platform summaries. Automating this specific sequence offloads the technical friction of publishing, removing the administrative tasks that typically lead to creative burnout. By structuring the workflow in this sequential, highly constrained manner, the architecture preserves the user's cognitive load exclusively for qualitative, human judgment. This method of context injection is not limited to publishing. In clinical healthcare environments, where accuracy is critical, this architecture scales to manage secure patient data. Ovira AI utilizes this approach to translate scattered, hard-to-describe patient symptoms into structured, doctor-ready medical reports. Handling this data requires rigorous security infrastructure, utilizing a Next.js frontend paired with AWS Cognito for isolated user pools. The foundation is an Amazon DynamoDB database layer with auto-expiring data protocols, supporting the AI core powered by Amazon Bedrock. The determining factor in this architecture is the health summary injection mechanism. Before executing any AI call, the system automatically pulls exactly 30 days of structured symptom data to build a rich historical context. Because the model processes this preloaded personal history first, it achieves true diagnostic resonance. It evolves from a simple medical chatbot into a precise clinical decision support tool. The most extreme testing ground for these resonant architectures is cyber-physical maritime automation. The Digital Captain framework addresses a critical flaw in autonomous shipping. It replaces brittle, software-only AI with system-wide physical reflexes. This technology is currently undergoing real-world development and testing on the open water. The core engineering problem is a conflict of timing. The system must handle slow, strategic planning while simultaneously executing split-second emergency physical reactions. The solution is a bifurcated cognitive architecture. The top layer is a goal-based agent, optimizing long-term voyage routes and ensuring strict compliance with regulations. The bottom layer is a perpetually vigilant reflex agent built for high-stakes, rapid emergency response. This reflex agent bypasses the strategic core entirely. It integrates directly with the ship's bionic actuation, sensors, thrusters, and robotic systems to deploy immediate physical mitigation. To ensure reliability, the system uses an STCW AI competency matrix, which translates established human competencies, like fire prevention and collision avoidance, into verifiable algorithmic data points. In unpredictable physical environments, safety requires structurally separating long-term strategic reasoning from anxious, rapid response vigilance. Across publishing workflows, clinical diagnostic models, and cyber-physical robotics, the ultimate goal of these systems is not total autonomy. The true operational endpoint of every resonant architecture is the human-in-the-loop handover protocol. The system continually feeds highly contextualized process data directly to human operators stationed at a remote operations center. The AI processes the massive volume of quantitative data and historical context specifically so the human operator can apply qualitative, intuitive judgment without cognitive fatigue. This introduces a new requirement for leadership. Human teams must be explicitly trained to manage, audit, and ethically deploy these complex systems. This demand is driving institutional scale in AI leadership education. Implementing AI requires treating the system like a new teammate. It demands strategic boundaries, continuous feedback loops, and strict ethical oversight to function securely. True digital scale is only achieved when enterprise system architecture is explicitly engineered to preserve, protect, and amplify human intent.